We don't say it's here, right? We say it could be here. I don't know, but there's a probability that it's there. So now it sort of has a probability cloud. Now it looks like it gets a little less, why am I drawing spirals? It looks like it gets a little less probable as you go further out, right? So maybe the density of probability, because look, right, it's got a peak there, but even if I just plot that first orbital, even as I go all the way out to here, it is non-zero, right? So this is probability, right? And this would be n equals 1. So it's a totally different story. That electron isn't in one place, but it is. But it's not. It could be anywhere. It could be, if I'm a hydrogen atom, my electron could literally be across the room. There is a finite probability that that's true. And we know that since we are all waves, and we can all be defined by the equations of quantum mechanics, and in fact that is the way to define the world, that we also have probabilities. They're small, you know, but I could be over there right now. There's a chance. My wave function is not exactly 0 all the way over there. It's close, but it's not exact, right? That is a very different picture of an electron in an orbit. In fact, it's not an orbit, it's an orbital. And that's where we say orbital. That's why we say, okay, but we're listing quantum numbers. These are the quantum numbers. Oh, I'm going all caps. I didn't even know I was going to do that. So we have n, which is called the principal quantum number. And this is going to be related to the main energy, kind of like, you know, E1, 1, right? E2, 2. So this is going to be related to the main energy level, right? And it's also related to the radial distance. And sometimes we call this the shell. So sometimes the principal quantum number, this is the shell, right? It's the first shell or the second shell, right? So we can call this the shell. Come back to that later. And you can see right there. Okay, we'll talk about n equals 2 and 3 in a sec. But, you know, let's talk about it now. You can see right there. If I go from n equals 1 to n equals 2, then I'm further out. Yeah, I still got non-zero. It doesn't quite go to 0, like I just said there, right? But it's further out. It's shifted out, right? So with increasing n, right? So another thing we can say about n is that with increasing n, you get higher energies, and larger distances, larger r. Oh, but you get something else. You get something else, and you can see it there, and I've been avoiding it, but I got to address it right now, because those higher n functions go to 0, right? So they have nodes. With increasing n, you get more nodes. What's a node? A node is when it goes to 0. And there's more of them. Now, that's also really important. So what that means is, it says in Bohr, my orbit was R, E. Heisenberg said, no way. Can't have them both. But I had an R, which was one value. And remember, it could only then be the R of the next value, the next n. Now, I'm basically saying the opposite. I'm saying, well, actually, R can be anything. There's a probability cloud. So this electron could be anywhere with certain probability, except not here in this one place, this node. It's 0. It's literally 0. The probability of finding the electron there is 0. It cannot exist there. But how bizarre is that? The electron can exist with probability out here and probability in here, but it can't exist in between. It's the same electron, right? Try explaining how it goes back and forth. It skips over a zero probability part, R, right? But these nodes are very important. And just to give you a sense of what this means, I found a very fancy animation because I want to make sure you guys understand. So here's the electron. It's doing this. It's doing its waving thing. But look at what happens at the nodes. The probability there is always 0. You see that? Can't go. No, not gonna exist there, right? That is super deep because there's no classical analog to these things. There's no classical analog. But this is what electrons do in an atom. Now, this is what the clouds look like, a little better drawn than mine, for n equals 1, n equals 2, and n equals 3. So again, you can see this is one electron. It's colored differently just to contrast it, but this is one electron, right? And these are, plus and minus of this, right? So it'd be like a wavy wave, and you're just showing plus and minus with the yellow and blue. But that node in between is where it can never be. But it's one electron. It's not many, it's one, and this is its probability distribution. Now, I want to make one really important point, which is that, look at what I'm plotting here. Maybe some of you, that's psi squared, right? So it's only the square of the wave function that we can relate any physical meaning to. The physical meaning I just related to you is the probability of being somewhere. That's what psi squared gives us, the probability of being somewhere. But ask your teacher, not me, your quantum teacher. Ask what psi means. And they're going to have it's going to be an interesting class. Force the issue. Don't let them go until they answer. We still don't know. We still don't know what the actual wave function means physically. We cannot attribute a physical meaning to it, only to its square. So we go about our business for the last 100 years, squaring it and saying, okay, well, it describes nature, that's great. But no one still knows what it means without the square. Right? I find that incredible. And it led Bohr to say all sorts of really cool things. He said, we must be clear that when it comes to atoms, language can be used only as in poetry. The poet, too, is not nearly so concerned with describing facts as with creating images and establishing mental connections. That's Bohr, like deep in it, trying to figure out what psi means. He's like, I don't know. It's poetry. Okay. That's cool. That's cool. V squared means something. V doesn't. Really? No. Classically, we got nothing. Right? Quantum mechanics. Oh, it's a beautiful thing. That makes me want to throw t-shirts. I got to do this. All right. I got to go. I know. I got to go backwards here. Okay. Hold on. Oh. I'm missing there and there. I know. I got to work on my arm. Yeah, and there. Show you love over there. Okay. All right. I'll have more on Wednesday. And the reason is we're making our first solid. I almost wanted to leave it as a surprise, but I couldn't help myself. It's extremely exciting. This is, after all, solid state chemistry, and Wednesday we're making a solid. Literally, we are not only making a bond, but we're making a solid and talking about solids. So that's going to be very exciting. And we're going to start by filling elements. But before we do that, I want to explain something very important, which is what's happening with energy, right? We did just see something dramatic. As you go from Bohr to quantum, something very dramatic happens with where, right? And we know something else very dramatic happens, which is right here. That's Bohr over there, n equals 1 around that. Bohr is 1, 2, 3. But look, you see, I'm now here at n equals 2, going from the Bohr model to quantum. I've got this, and I've got 3 p orbitals. right? And that's called degeneracy because you're taking something and you're saying there are multiple variations that have the same N. So what happens when we go multi-electron? And there's two effects that I want to explain. Here's what happens to this picture. Those are the 1 electron levels, right? There's Bohr over there. This is what you really get in terms of energy, right? This is energy along the vertical axis. And there's two reasons, two very important reasons, why these are so different. One is called shielding, and the other is called orbital penetration. And I want to talk about both of them in the last 7 minutes of class. I'm going over here. All right, so let's do shielding first, okay? Let's take an example. I'm going to give you an atom with 15 protons and 15 electrons. What atom is it? Anybody know? Phosphorus. So I'm going to draw them as rings, even though we know they're not, right? These are my orbitals. But I've got like an electron here, okay, an electron there. Because for n equals 3, how many electrons do I have left? 1, 2, 3, 4, 5. And you can already see what's happening. So remember, Rutherford told us this. All this charge is in a tiny little point here. You wouldn't even see it if we were drawing this to scale. Okay. But what are these electrons seeing? What are the electrons seeing? Well, you know, these inner two electrons are just seeing this huge amount of charge. They are happy. 15, but these out here, you see, these electrons, let's say those electrons in here, these shield the outer electrons, these shield outer electrons by 2 electrons, right? So because they're kind of in the way. It's like you got this negative charge that's in between me and the positive charge, right? And so if I'm out here in n equals 2, I don't see, right, 15 positive charges there anymore. I see 13-ish. That's shielding. And if I'm, right, so, but now this one, this has, you know, the 2s and the 2p electrons. It's got 8 electrons there, and those are shielding another 8. Those are shielding another 8 protons, right? So these ones have sort of an effective, Z effective, you know, that could be something like 5. This is not the Z of the atom, but it's sort of like those very outer electrons don't see the whole proton cloud. They get shielded. And that's a very important part of what happens to orbitals when you put a lot of electrons in them. And there's one more thing that happens, and it goes back to this plot that I showed you before, which is that the orbitals themselves are very different than just like a straight line from Bohr. They have these shapes to them, right? So the second thing that happens is that if I have that same S, you know, this is S, so this would now be the 1s, and now I'm going to put, remember that 2s looked like this, and it had the node there, remember that? That was 2s, right? But now we're going to put the 2p there. This may not be drawn to scale. Okay, here's the 2p. Something very, very interesting is happening here. And again, it has to do with what electrons are seeing. Because the 2s electron has a probability. Remember, this is the probability normalized, so we put an r squared there, right? That probability, all that means is if I integrate over everything, it's 1. It's got to be somewhere. But look, the 2s electron can be really deep inside the shells. It can be in there. Literally, look, it's even inside the 1s. So it gets some of that 15 proton action, right? Orbital penetration leads to massive changes. Orbital penetration is what this is called. And it allows some of but the P doesn't have that. It goes in a little, but the P doesn't have that peak all the way in there where it can see all that positive charge. And that is why these two things are different, you see? Because the 2s now can be closer sometimes to those 15 protons, right? And so it lowers the energy, making it happy. It finds a lower happy place, okay? So we're going to use this, and on Wednesday, we're going to take these things and we're going to fill them up and we're going to make our first solid. Have a very good rest of your day.